this lecture, going to discuss about the FFT introduction. So in discrete Fourier transform DFT calculations, we are going to use the formula for n point DFT x of k equal to 0 to n minus 1 x of n e power minus j 2 pi nk by n for k varies from 0 to n minus 1. Similarly, in inverse discrete Fourier transform, you can calculate x of n equal to 1 by n summation k varies from 0 to n minus 1 x of k e power j 2 pi nk by n. Here small n varies from 0 to capital N minus 1. So in this case, for DFT and IDFT calculations, the total number of additions required is n minus 1 addition, because here we are adding the 0 to n minus 1. So x of n, first for example, if you are substitute n is equal to 0, that is x of k equal to 0 means x of k, here k equal to 0, you are computing the x of 0. So here small n varies from 0 to n minus 1. So x of 0 e power 0 plus the x of 1 e power minus j 2 pi. So here k is 0 means everything is 0. So likewise n minus 1 times we are adding. So this process will be repeated for n times, because x of 0, then k varies from 0 to n minus 1, x of 1, x of 2 up to n minus 1. So the total number of complex additions required is n into n minus 1. Here the total number of complex multiplications required is n square, because the number of multiplication is n. This process will be repeated by n times. So the number of multiplications required is n square. So fast Fourier transform. So in conventional method, we are requiring the number of addition is n to n minus 1. Similarly, multiplication is n square. So we want to reduce the number of calculations. For that, we are going for fast Fourier transform. So in fast Fourier transform, here the DFT is computed with the decomposition of n point DFT into smaller DFTs. So for example, if you are having n point sequence, so this n point sequence we can denote it as r power m. Here we can say that r is a radix. So the sequence will be decimated into r point sequences. So first, for each r point, we are computing the DFT. So from the result of r point DFT, then r square point DFTs are computed. From the result of r square point DFT, compute the r cube point DFT. So this process will be continued until we reach the r power m point DFT. So here m is the number of stages for computation, r is the radix of the FFT algorithm. So in this, we are having the different radixes. So generally we are using the radix to FFT. This is the efficient algorithm for computing the n point DFT. So in here, the n point sequence is decimated into 2-point sequence. Then result of the 2-point DFT, we can compute the 4-point DFTs. From the result of 4-point DFT, we can compute the 8-point DFT and so on. So then comparison of FFT with conventional DFT. So for performing the radix to FFT, the value of n should be such that n is even. So here the total number of complex additions required is n log 2 log n base 2. The total number of complex multiplications is n by 2 log n base 2. So in conventional DFT, the number of complex additions is n into n minus 1. Complex multiplications required is n square. So for different values of n, we can see that first the number of additions required for DFT and FFT is, so in conventional DFT, if you are taking 4-point DFT, okay, the conventional method, the formula is n into n minus 1. So 4 into 4 minus 1 is 3. So 4 into 3, 12. In case of radix to FFT, if you are substituting 4, n is equal to 4 means here the 4 can be written as 2 power 2. So log 2 base 2 is 1. So the power 2. So 2 into 4, 8. Similarly for 8-point DFT, so here 8 into 7. So 56. additions are required. So here 8 point means 8 can be written as 2 power 3. So log 2 base 2 is 1. So 3 into 8, 24. See that similarly, if you go for n is higher number, so the number of additions required in the DFT, conventional DFT is shown here. So compared to that, in FFT method, the number of additions required is decreased more. See here, if you take in real-time applications, 64 point DFT means in the conventional method we are required 4032 additions are required. But in case of FFT radix to FFT algorithm, 384 additions are required. Similarly, the number of multiplications. See, in the conventional method, the number of multiplications required is n square. So, if you take 4 point means 16, 4 square will be 16. Similarly, 8 square will be 64 and so on. For FFT, n by 2 log n base 2. So, if it is a 4 point means, see, 4 will be denoted as 2 power 2. So log 2 base 2 is 1. So this 2, 4 by 2 is 2. 2 into 2, 4. Similarly, you can substitute in this formula. You can get the number of multiplications required in the FFT algorithm. So see here, compared to DFT calculation with respect to conventional DFT method, the number of multiplications required is more. So here it's reduced more. Okay. So in FFT, see if you 64 point DFT calculation, if you want to see in conventional method, we are having 4096 multiplications are required. But in radix to FFT, only 192 multiplications are required. So what is the difference and comparison between the DIF FFT and DIT FFT? So in the fast Fourier transform, we can compute in two algorithms. One is decimation in time algorithm. Another one is the decimation in frequency algorithm. What is the decimation in time and decimation in frequency? So in decimation in time algorithm, the time domain n-point sequence is decimated into 2-point sequences. But in case of decimation in frequency algorithm, the n-point sequence will be decimated into n by 2-point sequence, then n by 4, and obtain the in the frequency domain. So here the decimation is done in the time domain, that is in this input side. Here the decimation will be done in the output side because the time domain will be converted into frequency domain in case of discrete Fourier transform. Another difference is, see here, this is the simple basic 2-point DFT of the DIT FFT and DIF FFT. See, you can take 2 points A and B. So the output, the horizontal weights are upper one is +1, lower one is -1. So this cross arrow weights are unity. So see here the output at this 2-point DFT is, so A plus B into W2 power 0, where W2 power 0 is the twiddle factor. So W2 power 0 will be equal to e power minus j2 pi 0 divided by 2. That is the twiddle factor. Similarly here A minus B W2 power 0. So here the twiddle factors will be multiplied before addition and subtraction. So here in DIF FFT, see here A plus B. Here also horizontal weight is minus. So A minus B into W2 power 0. So in decimation in frequency FFT, the twiddle factor will be multiplied after addition and subtraction. So this is the one difference between DIT and DIF algorithm. Another one is, so in DIF, input is the natural order and output is the bit reversed order. And decimation in time algorithm, input is bit reversed order, output is the natural order. So two differences are there. One is the complex multiplication or twiddle factor will be multiplied before addition and subtraction in case of DIT FFT. In DIA FFT, it will be multiplied after the addition and subtraction. Here input is, see here, this is the DIT FFT algorithm, DIF FFT algorithm. So the decimation will be done in the input side, that is the time domain. Here the decimation will be done in the output side, that is the frequency domain. So here the input is bit reversed order, output is in the normal order. In case of DIA FFT, input is normal order, output is bit reversed order. Thank you.